Okay, so I want to now model the situation where a traffic light turns from green to red. So remember the traffic equation. I'm going to write it in conservative form as the t derivative of u plus the x derivative of u times 1 minus u equals 0. And remember, u is the density of cars, and 1 minus u is the velocity of the cars. And remember, our units are a little bit different. Velocity is a percentage of the maximum velocity, whatever that happens to be, and then u is a percentage of the maximum density, whatever that happens to be. But I'm going to call them density and velocity. So u is the density, 1 minus u is the velocity, so this is the flux. So this is going to be u times 1 minus u. That's going to be the f of u for this problem, which we'll need when we apply the RH conditions. So let me graph what's going to be happening here. So this is the t-axis, this is the x-axis. We're imagining there being a traffic light right here. And it goes from being green to red, like all of a sudden. Like imagine an emergency vehicle is passing through. We're going to assume that to the left of the traffic light, that is over here, we're going to assume that u is equal to anything. It could be anything, but I'm going to pick 1/2. I'm picking 1/2 because this gives us, that's what maximizes the traffic flux right here. So this is like the worst case scenario. We've got the maximum flow happening over here, and then the traffic light going from green to red all of a sudden. So u is going to be 1/2 to the left of the traffic light here. The cars that go through the traffic light are not, they don't have anything to do with what's happening here. So we're going to forget about those. And we're going to assume over here, well, the velocity is equal to 0. At the traffic light, the velocity is equal to 0. Well, remember, the velocity is 1 minus u. So this means 1 minus u is equal to 0. In other words, u is going to be equal to 1 at the traffic light here. For cars, I like to think about conceptually in terms of the velocity of the cars, rather than the density of the traffic, because at the traffic light right there, there's one car. So it's a little weird for me to say that the traffic density is at a maximum there, just because it's a little more, the fact that we're doing a continuum approximation to a discrete problem is really apparent in a case like that. So I like to think in terms of velocity and then translate that into density. So the velocity of the cars are 0 here at the traffic light, that's red. So that means the density is 1, since we've got u is equal to 1 minus v. V is equal to 1 minus u. Okay, so here's what we're going to do then. The first thing that we need to do is to record that information over here. So u of x0 is equal to 1/2, and this is going to be for x less than 0. And u of 0t is going to be equal to 1, and this is for t greater than 0. And so our Cauchy curve is going to be the negative x-axis and the positive t-axis. And note that we do have a discontinuity. U is equal to 1 here and 1/2 here, so it's not continuous at the origin where they meet. The next thing that we need to do to be able to look at the characteristics, we need to write this in expanded form. I'm not sure if it has a name. Again, if I do the chain rule on this, this is u minus u squared. If I do the derivative of that with respect to u, it's going to be 1 minus 2u times the x derivative of u is equal to 0. Okay. And then we're going to get our equations. So we're going to have t prime of s is equal to 1. Now the value of t of 0 is going to depend on whether we're looking at a characteristic that starts here, that is the t naught that starts on the positive t-axis, or one that starts on the negative x-axis. So x naught. Okay, so if we start on the negative x-axis, it's going to be equal to x naught. If you start on the positive, if you start on the backwards, t of 0, if we start on the negative x-axis, is going to be 0, and it's going to be equal to t naught if we start on the positive t-axis. X prime of s is going to be 1 minus 2z. This is just like we've set these problems up before. X of 0 is going to be equal to x naught if we start on the negative x-axis, and 0 if we start on the positive t-axis. And z prime of s is going to be equal to 0, with z of 0 being equal to 1/2 for the characteristics starting on the negative x-axis, and 1 for the characteristics starting on the positive t-axis. Okay, so let's look at the characteristics that start on the negative t-axis. In this case, we're going to have t of s is going to be equal to s. Z of s, well, z of s is going to be equal to 1/2 because z prime is 0, so z of s is going to be equal to 1/2. Look what's going to happen with x. If z is equal to 1/2, x prime is equal to 1 minus 2 times 1/2, so x prime is equal to 0. So x of s is just going to be equal to x naught. So they're just going to be these vertical lines, or I guess these vertical half lines. And again, this is technically only valid for x naught strictly less than 0, but I'm going to draw the boundary characteristic as a dashed line. Okay, now for the positive t-axis, we're going to have t of s is equal to s plus t naught. X of s will be equal to whatever it is. Z of s, well, what's z of s going to be? It's just going to be equal to 1. So z of s is equal to 1. This means x prime is 1 minus 2, so x prime is equal to minus 1. So this is just going to be minus s. So now the characteristics are going to be lines that emanate from the positive t-axis with a slope of minus 1. So stuff like this. And as usual, I will draw the boundary characteristic here with a dashed line. Okay, so again, what we see is that in the wedge between the dashed lines, there's ambiguity. It is not, what we have right now is not well defined. Okay, I like to think about it in terms of velocity, like I said. So if you imagine a car, for this value of time, if you imagine a car right there, the purple characteristic says that its velocity should be equal to 0, and the blue characteristic says that its velocity should be equal to 1/2. So what is the actual velocity of the car? Or sort of mathematically equivalent, what is the density of the traffic there? So let me get rid of this. So again, this is a situation where this is a physically reasonable thing. The setup is a physically reasonable thing to set up. Something happens in this zone right here. We need to know what happens. And we're going to use the RH conditions to figure out the shock location. So we're going to have some shock location. And remember that the conditions, xs prime of t, is going to be f of u to the right minus f of u to the left over u to the right minus u to the left. Okay, well, let's think about this. U to the right is equal to 1. The cars are stopped at the traffic light. So the purple characteristics, the velocity of the cars are going to be is equal to 0, so it means u is equal to 1. And the blue characteristics, u there is equal to 1/2. So we're going to have 1 minus 1/2. Okay, so f of u r. So remember, this is our f of u. So if you plug in 1 to this, you get 0 because 1 minus 1 is 0. If you plug in ul, which is 1/2, you get 1/2 times 1/2, so that's minus a quarter. Or it's equal to a quarter, but we're subtracting off a quarter. Okay, and altogether that's minus 1/2. So xs prime is equal to minus 1/2 if you do this computation. So xs prime is equal to minus 1/2, and then so now we have xs of t is going to be equal to minus 1/2 t. Well, the shock starts at 0, so it's just going to be minus 1/2 t. Or this is t is equal to minus 2x. So we're going to have a shock that goes like this. Okay, if I draw the characteristics, the blue characteristics are going to come up to it like this. And the purple characteristics are going to come to it like this. Okay. And so the solution, u of xt, okay, so what we're going to get for t, so this, sorry, this line here I should have written. This is t is equal to minus 2x. So to the left of the shock, that is for, let me write it like this. So we're going to have 1/2 over here. That's to the left of the shock. That's for x less than minus 1/2 t. And it's going to be equal to 1 for x greater than minus 1/2 t. Okay, so what we have is we have this shock that is propagating backwards at a speed that is 1/2 the maximum velocity. So let's say the maximum velocity is 60 miles an hour. If you start at the traffic light here and run backwards down the x-axis at 30 miles an hour, what you're going to see is that the cars, like this direction, or let me say, if you're going this direction, you're running 30 miles an hour in this direction, what's going to happen are the cars over here, like this direction behind you, are going to be stopped. And the cars up here are going to be going at, the density, are going to be going at velocity 1/2, 30 miles an hour. And then as you pass, the cars are going to slam on their brakes. And we see this is exactly what happens, or this is pretty close to what happens when you have cars suddenly stop, whether it be for a traffic light or some other reason. You have this people slamming on their brakes, this wave that propagates back down the road. And then, of course, you can imagine what happens. This wave propagates back. Let's say you're on the highway and a car slams on their brakes for whatever reason. The slamming on the brakes propagates all the way back to you. If there's a lot of cars, it's going to propagate far back to you. At some point, these cars are going to move forward. And when these cars start moving forward, the expansion wave that we talked about last week is going to propagate back to you. So you're going to have this initial shock followed by this expansion wave that happens. Okay, and again, you can think about this happens, these sort of like phantom wrecks or whatever you want to call them, where you slam on your brakes, you're kind of stuck in a traffic jam for a while, and then you don't actually see anything that happens. Okay, this is one of the things that can explain that. You have this initial shock wave that propagates back, that takes time, and then the expansion wave. And definitely it's going to take time if they actually have to do something and move the cars off the highway or whatever happens. But this is the equation that models that. Again, I like to think about things not necessarily, to me, when dealing with cars, I like to think maybe more in terms of the velocity. So the velocity is just 1 minus u. So in this case, the velocity is going to be 1 minus 1/2, which is 1/2 for x less than minus 1/2 t, and it's going to be equal to 0 for x greater than minus 1/2 t. It says ahead of this point right here, the cars are going to be stopped. Behind, the cars are going to be having, the normal 1/2 velocity. Okay, now we can always add different things to this model to sort of maybe if you are driving like maybe you ought to, and you see that people are slowing down in front of you, you're going to stop slowing down before the person in front of you slows down and things like that. Those are definitely things that we can take into consideration with more and more sophisticated models. At any rate, this is the very basic model for what happens when a light turns from green.